Number 1 says, determine the magnitude, direction, sense of the resultant for the coplanar concurrent force system shown. Use the parallelogram law. Sketch the force triangle. So I took the two forces and added them together. Here's the first one, 25, and here's the second one, 45. Number 1 is that one. 25 at 60 degrees, 45 at 10 degrees. Add them together tip to tail, here and here, and that produces the resultant and your force triangle. So this is the parallelogram law, right? Because I could also do this over here where we add this and this in the other order. So you can do it a number of different ways to make that triangle. 2 different ways makes the same triangle, right? We could go here and here for the other side, but that just makes it complicated. So I just draw one side, which is the force triangle, and then try to solve it. I almost always draw in X and Y axis at this location because I know things like the 10 degrees to horizontal, that was given for the 45, 10 degrees to horizontal, right? 60 degrees to horizontal. So I want those in. I want the 60 in, and then I did alternative interior angles to get 60 here. That and that are the same because this is a straight line. 10 here. So that gave me this inside because I know X to Y is 90, so 60 and 30, and 10, and this is 90, X to Y. That gives me the interior angle, which is what you need. You got to dig out an interior angle because we have two sides, 45 and 25. So if we can get side angle side, we can do the cosine law. Digging out the angle is the hard part. Draw the picture big. I drew it pretty big, and it could even be bigger, would be helpful, right? And then move these angles around and put in what you know. I know 45 is 10 to horizontal. I know the 25-pound force is at a 60-degree angle. So that means from horizontal 60, from horizontal 60. Horizontal to vertical is 90, so I know this is 30, and I just found the inside angle. 90 plus 30 plus 10, 130 inside. And that's all the way from here to here, right? Once you have that, you can put it together with the cosine law. R squared equals side squared, doesn't matter which side, plus the other side squared, minus 2 times both those sides, cosine the opposite angle, 130. Out. And I get an error because I can't see because of the reflection. That's rough. Try that. Anyone have a number? 64.02. Yeah, I get 64.002, which is just 0.0. Get those rounding to 2 places. Pounds. So that's the magnitude. I know the sense because things go together tip to tail, right? Adding these vectors. It starts at where you start and it ends at the last vector. So that is the sense up and to the right. I just need to know theta, the angle. So I know it's 30 out here. I don't know this interior angle. I'll call it alpha. And I don't know this, but I want to know that. So if I can get this, add it to the 30, subtract from 90, I get this. So we need one more interior angle. And I'll do that with the sine law. Once we have this and a side, right, we can get more angles. And I'll write it upside down. Sine alpha is over 45. So sine of the angle, opposite side. And then I'll use R again. 64.00213 over the sine of 1/3. That gives me alpha, which is this thing right here. Let's see what it gives me. So I get 32.5888. Carrying out a lot of precision within the problem, and in the end, I'm going to round it to. So now this plus this 30 subtracted from 90 gives me theta. Theta is going to equal 90 minus 30 minus 32.5886. 2741. Know the book got, Gina? Sweet. So the answer would be R equals 64.00 pounds at an angle of, that little symbol gives me the sense and the direction, 27.41 degrees.
Do you do R of A or just?
No, it's just the resultant of these two. And so this is okay notation. Oh, because this is point A? Yeah, that wouldn't be. Yeah, that'd be fine. Location of it.
Oh,
Yeah. But most of the time, like, we're gonna put everything together, including the graphics, so they're gonna know where it's at. Because your graphic is gonna be right next to your work, so. Yeah, that's the parallelogram law. You all like that more than the components, that's what I heard. I don't necessarily like it more than components. Cause you have to dig out angles, like you gotta get this 130 or you are sunk. You're stuck. You can't go forward. Unless you can build the triangle and get that inside angle. So that's why the parallelogram law is tough. It's not too difficult to draw the picture. It's sometimes difficult to get the angle inside that you need without making a mistake. All right, that's number one. How was number 3? I think it's the same thing, right? Yeah, they want you to do the same thing with these two. Find the resultant. That resultant ended up to be like down here somewhere. I started it. Oh, did I work it? I did work it. Want to see it? Look at it. So here it is. I did the 60 first, this one. Then I added the 75 to it, keeping it in position. And then that gave me the R value. So here's my 75 at its angle. Here's my 60 at its angle, 30. So again, I like to draw the XY coordinate system at this location and put in what I know. I know that's 30 if this is 30. Opposite angles, right? Opposite interior angles. I don't know this, but I knew this because of their little triangle they gave me. I could calculate it. 1/2 inverse tangent gave me 26.56 for this. So that gives me the whole interior angle at 56.5651. Boom. Once you get the interior angle, you got side angle side, you can go for the cosine. Parallelogram law. I already worked that one, so like educationally, I don't know if that actually helps because you just see it all at once and you don't kind of work your way through it. So we can work another one all the way through, but I had already worked that one out with the early breakfast club. No, we're not an early breakfast club. We need a different name than that. All right. So like he's getting grumpy now. He got up too early.
I don't get up at 6.
6.
Yeah, I got up at 6.
Days half over. Question is like, what angle do they want? So I don't know what angle the book is giving you consistently, but typically we want the angle of the resultant to the x-axis. That's the most common. To the y-axis is not incorrect. It's, in my opinion, just harder to find. So most of the time we want this theta thing to the x-axis, which means you just need this into your angle of your triangle, which is what I got here. Then do the whole 180 thing with the straight line. So 180 minus 30 minus alpha gamma gives you theta. So I got 76.61. Just to re-emphasize, R is the exact same effect as the 60 and the 75. That's why we do it. So after doing all this, the problem no longer would be 60 and 75. It would just have one force, R. And the effect is not changed. It's the exact same effect. So whether we use the 60 and the 75 or whether we use R, same effect. R is equivalent to the other two. There's going to be analysis we do where we want R. There's going to be analysis that we do where we want X and Y. There's analysis that we do where we use just the given forces. So we're going to want it in these different kind of modes. All right, that's 1 and 3. You also did what, 13, 17, 15, I don't know.
9, 10, 17.
9, 10, 17. Any questions on those? 17 will do for sure. What about 9 or the other ones?
The answer
For which one?
for
9. Oh, 9's the pole?
Yeah.
9's a fun one. Let's do 9. Find the resultant. Doesn't tell you how to do it, right? Just says find the resultant.
Oh.
So you can do it any way you want. There's 2 methods, component method or the parallelogram law. 200, am I doing the right one here?
Yep.
Okay. 200 newtons and 160 at some surveyor unit. This is shorter. 160 newtons. And then the angle is 41 degrees, 13 minutes. That one. This is 37 degrees. So which way, what was your preference? How'd you do it? You do it by the component method, where you add up the x's and you add up the y's, and that gives you rx and ry. Or did you do the parallelogram? Or did you just think about it? Components? You did components.
Yeah, but they-
Started on the components. All right, we've done parallelogram, so let's do components. Let's get this to its regular decimal angle. So that means we take the 13 and divide by 60 and add it to the 41. So 41.216 repeating degrees. Right? We do that first. Then we just pick away at the components. Which means there's a x component here and there's a x component here. So this is the fx of the 200. This is the fx of the 160. So we're going to collect the x of x and add them up. That's going to give us Rx, the component in the x direction of the resultant. Everyone see what I've done there? Started to draw the triangle of the components. So I'll finish the components. I'll draw the y component here, Fy of the 200, and I'll draw the y component here, Fy of the 160. And I'm even color coordinated. It's excellent. So we go for it. We got 37 inside. What do we have outside? 37, 90, 53, right? So in this triangle here, I have 53, or I can use the 37 right there. Either one. Inside here, I've got the 41.216. So do we use sine law, cosine law? Do we use trig functions, sine, cosine, and tangent? What do we do? Trig functions. We have right triangles, right? So this is just trig functions. I'll do this side first. I'll use the 37 since that's given. And that's here. So opposite side of the 37 is fx 200. So if I say sine 37, fx of the 200 over 200 newtons. Everyone see that? If you don't, you stop me. Say, what are you doing? That's gonna be 200 times the sine of 37. 120. And is that going positive direction or negative direction? Negative. This should be negative. That's how we're going to keep track of forces that are working together and forces that are kind of opposing each other. So I'm going to stick with finding x forces. I'm going to go for this one now. I know this is 41, so I'm going to use adjacent. That's cosine. So I use this triangle here to find the x. So I'm focusing on x forces. You get a lot of forces you're doing this with, they actually set up a little table, right? Where all the x's are in one side of the table, all the y's are in one side of the table, and then you can just add them up easily. So this fx of the 160 is equal to 160 times the cosine of that thing, 41. 120, 3569. And that's going which direction? Positive. So my Rx is equal to the summation of all of the x's, which is this and this. There's only two of them, right? And it's dang near zero, isn't it? It's close. Like when I do it, it's 0.00605. Yeah, so the bigger value is this 6.3 value here, and it's negative. Pretty close to zero. I'm sure the book just said zero for that. All right, so then we do the same thing for the y's, right? So now we're going to do summation of the y forces. This one is going to be for the y 200. It's going to be sine of, oh, I could use the cosine again. I'll use the 37. I don't have to do more math. Cosine 37 is Fy of the 200 over Fy 200 equals 159,727. Is that positive or negative? Negative. Negative because it is pointing down. And now we need this one, which is going to be sine of the 41. Equals Fy of the 160 over 160. Some 105. Four, 2, 3, 9. And it's also negative, pointing down, right? So this thing's down, this thing's down. This one is to the right, this one is to the left. I tend to add those vectors on too, just to keep track of what's happening. So then Ry. Everyone understand the whole Ry, Xy, or Rx, Ry? These are the components of the resultant. So the X effect and the Y effect, we need these often. So these are always pretty often calculated. R, so not so much. We don't really care about R that much, typically. We care how much side load we have. We care how much down load we have or up. That's what we really care about. So. All right, what do you get here? Well, these are additive, correct? Yeah, they're both negative. So 265.15. Is that rounded correctly? Yep. Newtons. Yeah. And I'm pretty much going to say, yeah, that's just vertically downward. The angle's pretty tiny. I think if you calculated the angle, it'd come up as pretty much zero, wouldn't it? Yeah. So this is real common. If it's vertically downward, you don't put an angle. You don't put it at an angle of 90 or something, right? You just point down and it's done. So R would be pretty much equal to R1. This is a excellent power line pole design. So power line pole design, we want the resultant to be within 2 feet of the base. This one happens to go straight through the base. That's perfect. That means there's no big bending load on those wood poles that we stick in the ground and put a bunch of wires on. Right? So we try to get power pole design to have the resultant straight through the concrete. Usually there's at least 2 feet of concrete down there holding those power poles up. So if that resultant can vary, you know, based on wind and all these other things, a little bit at the base, but we don't want it really outside the concrete. When it gets loaded with ice, like maybe you have trees over some parts of the power line, and then in the other section to the right of the power line, there's no trees, and that gets coated with ice. Now we have a side asymmetrically loaded power line pole, and it goes bad. Things fall over then. So, yeah. Questions? Is that helpful? All right, it's pretty quiet in here. Sorry, turn the music back on. How about another one? Any more of them? Any other questions on them, huh? 10? Which one is 10? Calculate the resultant force on the screw eye.
Yeah.
Ten is pretty much the same. Right? We have 200 pounds going this way, and we have 200 pounds at some angle. Correct? Am I right? This is the right problem. And then we're given rise and run again of 5 and 3 for our slope. And they want to know the resultant. One part of the rope is horizontal, so they're telling us that's horizontal. All right, so how many forces? 2 force. So our 2 force resultant strategies are parallelogram or component, either one, right? Both work. How do you want to do it? Component. So this is all in the X, correct? So for the 200, Fx of the 200 equals 200 pounds, the X component. Fy of the 200 equals what? 0. So whenever you see one force on the coordinate system that you're going to use, then you know the components immediately. Oh, this one, X 200, Y 0. This is negative, pointing in the negative direction. So then the only challenge is to find this one. This one has 2, down and over, right? Fy of the, ooh, I'm gonna need to, I'll make this prime. This one will be prime. So now this one is just 200. And Fx. Right? So we need an angle. I'll get that one, which is going to be the tangent minus 1 of opposite over adjacent. So I'll be doing this angle here, opposite 3 over 5, inverse tangent. The 30.9637. 30.9638. That gives me this. Then if I use the sine of this, I'm going to find this x component. Sine of the 30.9638 degrees equals opposite fx 200 over 200 pounds. Fx of this 200 is sine. I'm telling you, the reflection's brutal. 102. Eight, 9,915 pounds, and is it positive or negative? Negative. It is going negative. And then this y component is going to be cosine. 30.9638 degrees equals Fy 200 over 200. Fy 200 equals so 171. 7. 171,496. Down, right? This one was the left. This is negative. So now you have the x components of this creature and this creature, and they're working together, so that's going to go big, 302. So Rx equals 302. I can do that math in my head. 89915. Negative going this way. And Ry, this one is 0. So we just are using all of this one minus 171,496. That's down. Then what do we do?
Triangle and then do the.
Yep, Pythagorean theorem. Everybody knows how to do that, so I don't need to do that. Same problem, same kind of problem. Two forces, find the resultant. You're either going to use a parallelogram or you're going to use components. What if you had like 8 forces? Components. Parallelogram is out. Not an option with 8 forces. So, excellent. Let's do one more and then we'll take a break. So hang in there. We've got to do the moment one, right? It's the new concept. I'm pretty sure I drew the picture somewhere. Oh, there it is. 17, right? Yeah. So, and then we'll expand on moments in the second part of the class. What's the equation for a moment? Force times distance. It's about the simplest equation you're going to come across. Then why does it get so complicated? So notice I always put this perpendicular down for the distance. So I want to make sure you understand that forces have a line of action. All forces have a line of action. And we use the perpendicular distance from the point where you want the moment. If we want the moment at A, from here to that line of action, and it makes a right angle. That's what the perpendicular distance is for the 20. Okay, super easy to do when you have a parallel system because the distances are just given to you 4, 5, 6, 8, you just add them up. It's easy. Much harder to do when we have forces at an angle. So the moment at point A of the 20-pound force would be equal to 20 pounds times the distance from the line of action to the point, 4 feet. Yeah, agreed? All right, simple, easy peasy. What's that number? 8. And what's the unit? Foot-pounds. Torque. What's the sign of a moment? It's rotation, exactly. Totally different than the sign of a force. It's the sign of the rotation, the sign of the moment. It is the rotation that the 20 creates about point A. You can only see it if you draw it in, like if you attach the little string to the arrow, let the arrow go, then it rotates around the point, then you can come up with the sign. It's not whether the vector's pointing up or down. That's the sign of a force. It's what the rotation is, okay? And in this case, it happens to be pointing down and also creating a clockwise rotation, correct? So that is negative. Clockwise is negative. Counterclockwise is positive. This is, and I use the symbol probably more than I use the negative. So I don't always put the negative in front of the 80. You can, perfectly legit to do it. I just keep track of the rotations. That's what you have to keep track of. All right, so then what's the 40? 40 times 9, yep. 360? What's its rotation? Yep, negative. What's the 50? 50 times 15, right? Can't do that in my head for some reason. Sounds good. 750 foot-pounds. And what's its rotation? Positive. Counterclockwise. Simple. They really are. Parallel systems are simple. Then I think it had you sum them up, right? Just keep the sign right and sum them up. No problem. I don't know, would you all get 380? Positive or negative? Which is negative. 380 negative, I'm hearing, and I'm seeing some head nods, so confirmation. The engineering firm is convinced that it's 380. We're all going down together when it all falls over. It's such a wonderful feeling, isn't it? All right, let's take a break. And then we'll talk more about this. All right, let's get a little more complicated with a force at an angle and trying to determine the moment. So here's where I'm going to emphasize this formula: force times distance perpendicular. If you're going to use the equation directly, like force times distance, then that distance has to be perpendicular to the force line of action. So the force line of action is here, and you can draw it in with every force that you work with. And we can move that force anywhere along its line of action. The effect does not change. It's the old push the car, pull the car concept, okay? So to get the moment of this force, if I want to use this directly, I have to use the perpendicular distance to the point that I want the moment. So if I want the moment here, I have to make this right angle with the line of action that goes through the point. Right? 90 degrees. That is the perpendicular distance. Perfectly fine to do it this way. It's just called just driving the formula. I'm going to use the formula directly. Okay. It means you have some trig to do. If this 60 is here, where is it inside the triangle? Yeah, it's equal opposite angles. So we have a straight line, we have a horizontal line, and you can reflect that angle into the triangle. So it's 60 here. Everyone see that? It's a good thing to be able to dig out because you got to have it. We would need a distance. So they would give you a distance on the problem, 10 feet. Right, so now we have a right triangle and we can solve for our perpendicular distance. Agreed? All right, go for it for me.
Hypothetically, didn't calculate that, right?
No, the 10 would have been given in the problem. Sorry, I should have had it on there originally. Yeah. They're going to locate forces for you. So I'll use so notice I'm working with distances, so I'm going to calculate a distance. So sometimes students get confused like, oh, sometimes he uses sine to get a distance, sometimes he uses sine to get a force. That's true. Depends on what the triangle is you're working with. And this is a distance triangle. I'm using the line of action of the force, but I'm not using the 700 pounds at all, right? I'm just trying to calculate a distance, the perpendicular distance. .66. 0203 feet. Does that make sense? Should it be smaller than 10? Yeah, that makes sense. 10's the hypotenuse this triangle, right? So now I can say, oh, the moment is, what's the force? £700. And what's the perpendicular distance? 8.6603 feet. Moment of A of the 700 pounds equals 6495. 0.19. What's the unit? Foot-pounds. Because we multiplied pounds times feet. You can say pound-feet. Doesn't roll off my tongue as nicely as foot-pound, so I say foot-pound. But it's the same thing, right?
Were you just multiplying the 700?
Yeah. Yep.
Yeah.
Force times distance. Uh-oh.
I got 6,062. Yeah, 0.2.
How could that be?
I don't know.
8.6603 times. I get 6062. Oh, wow. Where'd this 6495 come from? Sorry. That's why you all are part of the firm. That look better? Thank you. And what else do we need for a moment? Rotation, exactly, rotation. So we have to figure it out. Forces on an angle, sometimes they're complicated, especially if the line of action goes really close to the point that you're doing your moment about. This one's not very far. I mean, this one's quite a ways away from the point, so we can kind of see it, at least I can. What I do is I move the vector down closer to where the perpendicular distance is, attach the string, let it go, and I get the rotation. Right, so however you do it is fine. Is that clockwise or counterclockwise? Yeah, it's a negative. That's clockwise. Excellent. So Verganon, this theorist, he came up with the theory that, hey, there's other ways to do moments. Right? You can do moments this way by the formula directly. You just have to be very careful with the perpendicular distance. Or you can do moments with the components of a force. And it'll be the exact same. Because components are exactly the same as the original force, 700. So you can also take the 700, get rid of it, put in the X and Y component of the 700, and then find the moment of both those forces. There is advantages to it. Right? If I know that I have a Y force here, and that's the Y component of 700, if I'm going to find the moment of this, what perpendicular distance am I going to use? The 10. It's straightforward. And then what about the X force? Where's the line of action going? Straight through the point. It creates no moment. No rotation if it goes straight through the point. It's like pushing on the hinge of the door. Doesn't work, right? So often one of the components just drops out. Like you don't even need it. All of the moment, this is interesting. All of the moment of the 700 is created by the Y component. That's kind of weird, but it's true. So really, the X component drops out, does not create any moment. All you need to know is the Y component and its perpendicular distance. So let's verify that. Let's get the Y component. The Y component, it's also here, right? If you're going to draw them here, it's also over here. And the 60 is up here. However you want to do it, but it's opposite. So it's going to be sine 60 equals Fy over the hypotenuse 700. Now I'm dealing with forces, 700 pounds, the Y component, and the angle 60. Fy is equal to what? Yeah, it better be. And my calculator just died. I'm relying completely on you now, so I'm super stressed out. 60 should be 606. I can write this 221, right? Yeah, keeps going, but so that's the component, correct? And then to get the moment of this component about this point, I would multiply by 10, which just moves the decimal over, which is exactly what we had before, equivalent. That's because the components are equivalent to the 700. So the moment of this plus the moment of this is going to be equivalent to what we calculated the first time. That's what this Verganon dude figured out. It's like, hey, you can do the moments of the components, or you can do the moments of the original force, whichever way you want. So there's advantages to knowing that, because if you have a problem like this, where we have some kind of structure thing, then we put a force on it, and then we want to know A, and you know all these distance 4, 10, and 6 feet, right? And 4 feet and 8 feet. And this is like 200 newtons at 60 degrees. And I want to know the moment at A.
Does, how you protect it?
Sure, absolutely.
You try to find the distance from point A.
Well, let's look at both methods first. Let's say, okay, we want to do this by the formula directly. I want to know where the perpendicular distance is to this line of action. Well, it's right here. Easy to draw. Agreed? Perpendicular distance to the 200. Right? How easy is that to find? It's not. You can't. Like, you could maybe draw it in AutoCAD and find it, but like mathematically, the number of triangles you'd have to make to find this is ridiculous. So that tosses out the formula directly and says, "Oh, don't do it that way. You're never gonna find this thing. It's rough." Instead, if we could find this component, put it in red, Y component. And if we could find the X component, then the distances are easy for those two moments. What's the distance for the Y component? Yeah. Remember, we just say, oh, here's the line of action. Right, and then here's the perpendicular distance for the red. And it's 4 plus 10 plus 6. 20 feet. That makes sense? Now, I didn't draw this to scale, so I'm not sure how this is gonna work, but what's the distance here, right? So here's the line of action. Of this one. And here is the perpendicular distance of the green force. This one is of the red force. Yeah, so it comes down 4 over, it goes up 8. So that's 4 feet, pretty simple. So as long as we can do our trigonometry here to get those two components, we can get the moment easy of this 200 about point A. Where finding that distance is like, that's a nightmare. Okay, so that, I mean, this is why we have this second method. We can always find the moment by the components. What you have to be good at, become good at, is drawing in these line of actions and figuring out the perpendicular distance, right? That's important. Regardless of the position of the problem. So, like telephone problems, they're vertical problems. It's kind of sideways forces, right? So then we work with up and down distances for moments. Beams are horizontal problems, and then forces are typically up and down, so we work with these distances horizontal. So you just have to like really think about like, oh, what's the perpendicular distance between this force and that point? You really need that line of action to then say, oh, that's the perpendicular distance. Same with this line of action and this perpendicular distance to A. Let's see if, did I give you 33? Give you something like this. Uh-oh, wrong class. No, I did not give you 33. 33 is on Monday. Okay, so we're good. 24 and 25 is your homework. And you are totally prepped for that. 25 is definitely gonna be a problem that you're gonna wanna use the components on. It's gonna be easier to do components, so. 24, I think, is also easier for components, but you can do it either way. However you wanna build that triangle. Good? Chapter 3, yeah, we are focused on chapter 3. Your quiz is up and available. So you just find it on the day. Today is, why is it blank? I feel like I'm in the wrong class. Oh, there it goes. Friday, there it is. And there's your quiz. Just work chapter number 14 out of chapter 3. Work it separately. It's not a together thing, but you do have all day to do it, so. And then submit it. So Cam Scanner submit to Blackboard. Oh, Juan, you're always creating problems. Yeah, you can hand it in to me. If you're gonna work it in here, then just work it on your own. I wanna know you can do it. All right. We're officially done. I'll be in here for the rest of the day, pretty much. So.
Sure.